Welcome, and this lesson is going to be about numerical approximation to integration. I'm going to present 5 methods that you may make use of when you are faced with an integral whose solution you're having difficulty finding, likely because none of the integration methods that you've learned prior to this, such as U substitution, trig substitution, partial fractions, are working in order to yield an exact solution. So when you're faced with a scenario like that, then you may want to approximate a solution. You also need a definite integral. You can't do this for an indefinite one. So you should read the first page of this handout, which describes all 5 of the approaches. To summarize, methods 1 and 2, the left and right endpoint rules, essentially split the area under the curve that you are trying to integrate into rectangles. The left endpoint rule creates rectangles where the left endpoint of the rectangle touches the curve. The right endpoint rule creates rectangles where the right endpoint touches the curve that you're trying to get the area underneath. The midpoint rule creates rectangles where the middle of the rectangle touches the curve. The trapezoidal rule creates trapezoids where both the left and right points of that trapezoid touch the curve. And Simpsons rule essentially generates a parabola that estimates the curve. So you're going from 3 horizontal lines like a histogram for the left, right, and midpoint rules to a slanted line potentially, a line with some slope in the trapezoid rule. And then the 5th one approximates the curve with a parabola. I'm going to present this more intuitively, and I'm going to use the exact same problem for the rest of this handout to demonstrate how to apply each of these approaches. The problem is finding the area under the curve square root 1 plus x cubed between -1 and 1. And we want to do this using n equals 6 subintervals, which is just another way of saying rectangles. Now, in order to figure out exactly how wide those rectangles should be along the x-axis, there's a very simple approach, and that is to look at the right bound minus the left bound divided by n, the number of subintervals that you want, which is right here. So we are going from 1 minus -1 divided by 6 subintervals or rectangles, which comes out to 2/6, which simplifies to 1/3. So where does this come into play? Now I happen to know what this curve looks like. And I'm going to do a sketch over here. And the curve looks like this. And so this is our function square root 1 plus x cubed over the interval from -1 to 1. What we just discovered with the 1/3 is that we are going to create rectangles with endpoints at 1/3, 2/3, 1 on the right side, 0s in the middle, -1/3, -2/3, and -1 on the left side. So this is going to be our general format, and you can see that you've got 1, 2, 3, 4, 5, 6 subintervals. And so it's within those subintervals that we're going to create rectangles. Let's start with the left endpoint rule. So the left endpoint rule creates rectangles where the left side goes up to your curve. Now it just so happens that the left side touches the curve at 0 in the first subinterval. And so it's just a flat rectangle or a line. Whereas in the second bin, it touches at x equals -2/3. For the third bin, it goes up and touches For the fourth bin, it touches at x equals 0, and you could continue the pattern. And you could see that if we get the area of all these rectangles, every rectangle in this example, it's not always true, but in this example, underestimates the area. So the estimate of the area is going to actually have a shortfall with the left-endpoint rule for this method, but it's an approximation, so let's go through and actually figure out what that area is. So the left endpoint, based on 6 subintervals, I'm using L sub 6 to represent that, is going to be the area of the first rectangle, which has a height of 0 and a width of 1/3, plus the area of the second rectangle has a height of, and so we want to figure out what is the curve at -2/3. So this is f of -2/3 times a width of 1/3 plus f of -1/3 times a width of 1/3 plus f of 0, which is pretty quick to get. If you plug 0 in for x in the square root of 1 plus x cubed, you get the square root of 1, which is 1, times 1/3 for the width. And continuing on, we've got f of 1/3 times a height of 1/3, or sorry, width, plus 1 more, which is f of 2/3, times the width of 1/3. And that is going to give you the area of the 6 rectangles for the left endpoint rule. As we progress through, we are going to get 0 times 1/3, which is 0, plus when you plug in -2/3 for x in the integrand function, you get 0.8389. So that's going to be 0.8389 over 3 plus f of -1/3. So when x is -1/3, 1 plus -1/3 cubed, and take the square root of that is 0.9813 times the 1/3, or divide by 3. If you are not getting those two numerators, be careful with your calculator, because if you don't put the -1/3 and -2/3 inside parentheses and then cube it, it may not do it correctly. So just make sure you're using your parentheses. Plus the next one is 1 times 1/3, which is 1/3, plus f of 1/3 is about 1.0184 over 3. And the last one, f of 2/3, is about 1.1386 over 3. And when you calculate all of these, you get a left endpoint approximation of 1.6591. And from our picture, we know that the area, the actual answer, is a little bigger than that. We don't know how much, we just know it's larger than this. So this is an under approximation of the true answer based on our sketch. Now the right endpoint rule has a similar idea, except now the right endpoints of the rectangles have to touch. So I'm going to do these rectangles in green. And I've got, let me make it thicker. Here we go. Ooh, that went a little awry. Why is it doing that? That is funky. All right, let me do this. Okay, and then the next one looks like that. The third one is about there. Fourth. The fifth rectangle, and the sixth one is about there. And so in this case, you could see that more often than not, or always for this example, the rectangles contain too much area. So the answer that we get here is actually going to be an over approximation of the truth. So again, the visual is helpful in understanding about how your approximation is going to compare to the true answer. But let's go ahead and figure out what the approximation is. Obviously, it's going to be bigger than the left endpoint approximation for this particular example. So let's figure out what it is. So this is a right endpoint approximation based on 6 subintervals. For the first one, we have, so since the width is always going to be the same, I'm just going to factor out the 1/3 for simplicity. So right endpoint is going to be based on the value of f at -2/3 for the first rectangle, plus f of -1/3 for the second rectangle, plus f of 0, which we know is 1, plus f of 1/3, plus f of 2/3, and plus f of 1, which is also another pretty quick one to get. So that's going to be the square root of 1 plus 1, or the square root of 2. And a quick check, 6 subintervals means we should have 6 values here. So we've got f, f1, f root 2. So that's going to be 6 values. So we haven't missed any interval or rectangle, which is good. Then when you use your integrand function, remember f of x is the square root of 1 plus x cubed. So when you plug in and evaluate each of these functions, you've got 1/3 times f of -2/3 is about 0.8389. F of -1/3 again is about 0.9813. Plus f of 0, which is 1, plus 1.0184 about for f of 1/3, plus f of 2/3 is about 1.1386, plus the square root of 2, which is about 1.4142. And when you compute this, you get an approximation value of 2.1305. So we know, based on our sketches, that the true answer is somewhere between those two values, 1.6591 and 2.1305. So then you might say, well, instead of doing left or right endpoint, what if you did a midpoint? Maybe that's a little better, because your midpoint sketch, and I'm getting a little crowded here, but I'll do it in red. So the midpoint sketch means that the rectangle should touch in the middle of the interval. So your rectangles are going to look like this. And so this is often an attractive approach because it's a decent compromise for having some of the rectangle with too much area and some with too little. So it's a nice give and take instead of always being over or underestimating. And so you could see that for most of these rectangles, it's pretty obvious. For example, in that first rectangle on the left, it's taking some area on the left side of that rectangle that shouldn't be there, but it's also losing some on the right side. Not necessarily an equal amount, but it may be capturing an estimate of the area in that interval better than the previous two methods. And so this midpoint rule is an attractive approach for that reason. And it's still rectangle, so you still want a length and width. So in this case, let's go through and figure out an estimate for M6. Again, I know that the widths of these rectangles are always going to be 1/3, so for simplicity, I'm just going to pull that out or factor it. And the first midpoint occurs at f of negative 5/6. So if you have trouble figuring that out, you could always take the average of -1 and -2/3, and you'd get negative 5/6. Likewise, if you want the next midpoint, take the average of -1/3 and -2/3, and you'll get negative 3/6 or -1/2. But just for you to see the pattern, I'm going to write it as f of negative 3/6 plus f of negative 1/6 plus f of positive 1/6, f of positive 3/6, and f of positive 5/6. So a quick check. We've got 1, 2, 3, 4, 5, 6 values that we're going to have, which means all of our intervals are covered. And now we need to find out the y value on the curve at each of these particular values. So negative 5/6, negative 3/6, negative 1/6, and so forth. When you do that, what you should get are the following. So at f of negative 5/6, that midpoint value on the curve is 0.6491. At negative 3/6 or negative 0.5, you should get an f value of 0.9354. At negative 1/6, you're about 0.9977. At positive 1/6, it's 1.0023. Then 1.0607 about. And finally, 1.2565. And when you compute this, you get an answer that's in between the previous two, which is 1.9672. And so that's likely closest to the true answer for the integral that we are trying to approximate. At least based on our pictures, it looks like it may very well be the best estimate. So we've got two other approaches to look at. So let's consider the trapezoidal rule. Now, the trapezoidal rule does essentially split the intervals instead of rectangles. It splits them into trapezoids. And if you know the area of trapezoids or the formula to get the area, you could follow the same idea that we've been doing. But there is an alternative approach based on the path that we've done so far, which is that the trapezoidal rule happens to come out to the average of the left and right endpoint rules. So while we could get the answer as 1/2 base 1 plus base 2 for each of the trapezoids times height, the general rule of thumb is that this is going to be f at, let's see, for this particular problem, f of -1 plus 2 times f of -2/3 plus 2 times f of -1/3 plus 2 times f of 0 times the width of each of these trapezoids. And so the basic pattern, notice, is that the start of the support that you want to find the area under essentially begins with a coefficient of 1, and the end also ends with a coefficient of 1, and all of the internal coefficients are 2. And so that is how it's going to work. And so this is going to give you essentially the sum of your base 1 plus base 2's. The 1/2 comes from 1/2 base 1 plus base 2, and the height, or the width of your subintervals, is going to be 1/3 for this problem. And so that's where that part comes from. You can use this again in order to get the answer, but a nice shortcut is just 1/2 times L6 plus R6, which we got in parts 1 and 2. And if you take the average of your left and right endpoint rules, you get an approximation of 1.8948. Finally, we get to Simpsons Rule, which is a bit uglier to do manually, but if you are dealing with an even number of subintervals, there is a nice shortcut approach. In particular, that is described, or was described, right here, that it is a weighted average of your trapezoidal and your midpoint rules. And so in our case, we want S sub 6, which means 2n has to be 6, which means n must be 3. And so let me write that down over here. So we want S sub 6, which is going to be 1/3 of T3 plus 2/3 of M3. Again, just to highlight that, so we want S sub 6, we want the estimate Simpsons approximation based on 6 subintervals, which means that n is going to be 3. So that's why we're using T3 and M3. Now we don't have those, but we have experience with getting the trapezoid and midpoint rules approximations. And so it's pretty quick to get everything that we need. So let's go through the whole process again. I'm going to do a quick sketch of the curve. And based on 3 subintervals, we've got that our width, or the change in x, is going to be 1 minus a -1/3, which is going to be 2/3. So when you step to the right of -1 2/3, we get to -1/3. When you step to the right of -1/3 2/3, you get to +1/3. And when you step to the right of 1/3, a size of 2/3, you get to 1. So these subintervals account for 3 subintervals with a width of 2/3. So now we're going to go through and we're going to get our left and right endpoint rules. You should pause the video and see if you are able to get those on your own. I'm going to continue, but when you're ready, feel free to restart so that you can hear what the answers are and check yourself. So L3 is going to be 0 times 1/3 plus the area of the second bin is going to be f of negative 1/3, which was 0.9813, times a third, plus f of 1/3 was 1.0184 times a third. And this is going to give an area of 1.3331. Now we need the right endpoint rule. The right endpoint rule is going to be 0.9813 times a third plus 1.0184 times a third plus f of 1, which is the square root of 2 times a third. And this gives 2.2759. Which brings us to our trapezoid approximation. Remember that the trapezoid approximation is the average of your left and right endpoints. And so when we do the average 1.3331 plus 2.2759 over 2, and if you didn't approximate to 4 decimals, you could get even more exact, but I got 1.8045. And then we need our midpoint approximation, M3. So the midpoint is going to be at negative 2/3, which is 0.8389, with a width of 2/3. And that reminds me, all the 1/3 that I previously put should be 2/3. I apologize, because all the bin widths are 2/3 now. And then continuing with the midpoint approximation, the second interval has a midpoint at 0, so that's going to be 1 times 2/3, plus f of 2/3 is 1.1386 times 2/3. And this approximation is 1.985 about, which now brings us to s sub 6, which is 1/3 of T3, which we got to be 1.8045, plus 2/3 of M3, which is about 1.985. And this weighted average is about 1.9248. And that's it. This is a demonstration of 5 approximation methods: left, right, and midpoint rules, the trapezoidal rule, and Simpsons rule. It's fairly subjective as to which one you may use for any instance. Left and right and midpoint rules are fairly easy to do. Trapezoidal rule isn't too bad. Simpsons rule is the hardest, but not too painful if you're using an even number of subintervals. Good luck and enjoy.